Okay, let's start off. In week 13, we're going to start with chapter 6, the last chapter of our course. We're going to look at Riemann sums, and you may recall that we already looked at this back in section 2.6. So here's an example just to start us off. Let's think about work. Work as a physics concept is defined as force times distance. So for example, if you lift 20 pounds 8 feet off the ground, that's the same amount of work as lifting 10 pounds 16 feet off the ground or 40 pounds 4 feet off the ground. That would be 160 foot-pounds of work. Okay, so for the module question, we have you're pushing a weight for 20 feet, you are exerting 20 pounds of force, and then you have to push it up incline for 10 feet, and to do that you have to do a greater force, so you have to exert 50 pounds of force for that. At the end of traveling that 30 feet, how much work have you done? Okay. Here's a trickier problem. So we've got a 2,000 pound anchor at the end of a 30-foot chain, and the chain weighs 40 pounds per foot. And we've got getting a motor to lift this up off the ground. So everything's clear of the water. Don't have to worry about that. We're interested in how much work is being done in lifting up the chain and the anchor. Now, the thing that makes it a tricky problem is as the chain's being pulled in, the chain gets shorter and shorter, and so weighs less. Okay, so how would we go about doing that? So this is kind of like an estimation problem, and we've been doing that all semester. So the first guess is, the anchor's 2,000 pounds, the chain is 1,200 pounds, 40 times 30. So we just multiplied 3,200 by 30 pounds, we get 96,000 foot-pounds. Now that's an overestimate, right? Because as I said before, some of the chain has actually moved less than the 30 feet. So let's do a second guess. Let's consider the chain as 10 equal parts of 3 foot each. So that's 120 pounds each. So the work would be the work of moving the anchor, plus work of moving the first part of the chain, plus the work of the second part of the chain, blah, 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 etc. The work of moving the 10th part of the chain. So we just plug in the numbers. So 2,000 times 30 for the anchor, 120 times 3 for the first 3 foot bit, 120 times 6 for the second 3 foot bit, 120 times 9 for the third 3 foot bit, and 120 times 30 for the 10th bit. And if we do all that adding up, 60,000 foot-pounds to move the anchor, and 19,800 to move the chain. So that's a total of 79,800 foot-pounds. But that's an overestimate, right? Because we assume that each 3 foot bit of chain has moved the whole distance. So we could go the other way. We could deliberately underestimate. So we could do it from the top of the 3 foot segment. And so we get that sum there. So we start at 120 times 0 for the chain and end up at 120 times 27, because the last 3 foot chain, the top moves 27 feet. And if we do that computation, it's still 60,000 for the anchor, but now it's 16,200 foot-pounds for the chain. So that gives 76,200 foot-pounds. As I said, it's an underestimate. Classic thing to do. You have an overestimate, you have an underestimate, you just average the two, and we get 70,000 foot-pounds. We know how to get estimates. We just take finer and finer slices. So let's say we have 100 equal parts of 12 pounds each. Each, is like 0.3 of a foot. And so the work is just do the same computation, except now instead of 10 bits for the chain, we've got 100 bits for the chain. And then this time we go through the whole procedure. We get 18,180 foot-pounds as the overestimate for moving the chain, and 17,820 foot-pounds as the underestimate. Sorry, that should be read underestimate for moving the chain. So averaging all that together, we get 78,000 foot-pounds for moving the chain and anchor. Well, that's the same as what we got for our second guess. So I'm now super confident that the answer is 78,000 foot-pounds. So we solved this problem. Like, as I said, we've seen this kind of problem before. Back in section 2.6, we had a look at energy. So remember, energy is power times time. And that's when we first brought up the idea of the Riemann sum. So here we had this graph here. We had the graph of the power function, how it's been used over time. And so we approximated the power function as a step function. And we estimated energy consumption for this approximation. So for the first 6 hours, we estimated 28.5 megawatts of power was being used. So the energy used in that 6 hours is 6 times 28.5. And then we add 3.5 times 47, plus 5.5 times 75, plus 6 times 88, plus 3 times 57 to get our approximation. And again, we know the way to improve the estimate is by choosing smaller step sizes. Sorry about that typo. Okay, so here's the procedure for a Riemann sum. So to estimate any quantity which is defined as a product, so f of x times x over some interval a, b, so x goes from a to b, and it's some quantities that if f is a constant, you just do, you just do height times width or whatever. But we have the problem where one of the things is varying. So what we do is we estimate a number of subintervals, let that be n. They can have arbitrary widths, so delta xi, so we get delta x1, delta x2, all the way up to delta xn. The only thing is, it's got to cover the whole interval. So the sum has got to be b minus a, right? Because remember, the interval goes from a to b. We then got to sample the ith subinterval at some point xi. Okay, and so you let f of xi be the level over this subinterval. And so then we have a product for that subinterval, right? Because the quantity is defined as some kind of product. The heights are varying, but we just add up all those things, and that gives us an estimate. And if we want a better estimate, we just do a smaller, a finer sampling. Okay, so obviously, you want to do an Excel file after a while once it gets too, computations get too much. So it's easier to use the summation notation with all this. That's the sigma notation. So the Riemann sum is, so sigma means sum. We have I equals 1 to n. So I is the kind of like the variable that's counting for you. 1 is the starting point and n is the end point. So it's f of xi times delta xi. Usually we handle the decomposition of the interval by having all the subintervals be equal. So, if we're doing something where we're given some function, so it's easier to automate it if you just make each delta xi the same. So it doesn't really depend upon I, it's just a delta x, it's the same subinterval for the whole thing. And so that's just going to be b minus a divided by n. And so the Riemann sum then is going to be the sum of the fxi's times the delta x. You still need the sampling points. An easy way to do the sampling is either to use the leftmost point of the subinterval or the rightmost point of the subinterval. And then if we do both, we can average the answer to get good approximations, just like we did with the work problem at the start here. Right. Ignore that last point. Okay, that's it. And I'll be back later in the week with more examples of Riemann sums.